Okay, so we are going to look force analysis with motion practice problem number 2. And it reads, a 30-06 bullet has a mass of 0.01 kilograms. If the average force on the bullet is 9,000 newtons and the barrel length of the gun is 0.75 meters, so 75 centimeters long gun, how fast is the bullet going when it exits the gun? So that force is going to be exerted over the entire 0.75 meters. How fast is it going when it exits the gun? All right, how fast? That's a kinematics question. So we're going to start with the kinematics process. So the object, well, that's the bullet. That's the object that's moving. Kinematics asks us what starts what we care about, what ends what we care about. So it starts when the force is applied, when the bullet is being shot from the gun. So within the barrel, but starting to move. When does it end? When it exits the gun. All right, so let's draw our picture. Here's our gun, and the bullet starts at this point, and we'll call that point the origin, so where the bullet is within the gun. All right, in kinematics, then we look at our known variables. So we have x initial, x final, v initial, v final, acceleration, and time. It's always important to think, are we in one dimension or two dimension? We're in one dimension. It's just traveling along in a single dimension, the length of the gun. So where does the bullet start? Well, it starts at the origin, as I've defined it. Where does it end? Well, the length of the gun is 0.75 meters. So this point is at 0.75 meters. So it ends when it exits the gun and 0.75 meters. How fast is the bullet moving when it starts? Well, it starts at rest when that first force is initiated. And how fast is it going when it exits the gun? I don't know. The acceleration? We don't know. Time? We don't know. All right, so we want to know how fast. V final. That is our object of interest. So how fast is it going when it exits the gun? Well, we know that V final is equal to V initial plus acceleration times time. V final is our variable of interest. V final equals V initial. Well, V initial is 0. Plus acceleration, don't know that, times the time. Darn it, I don't know the time either. Well, then time sort of and acceleration become a variable of interest. Maybe I can get those from the position relationship. Okay, well, let's go after time. From position, I have x final is equal to x initial plus v initial t plus 1/2 a t squared is my position relationship. Well, x final, okay, that's 0.75 is equal to x initial, that's 0, plus v initial, well, that's 0 times time, plus 1/2, I don't know a, I still don't know t squared. If I knew a, then I would be able to get time. If I knew time and a, I'd be able to get v final. So I need acceleration to get this problem. Well, this tells me I need acceleration. Acceleration was something I needed up here too. Well, if I need acceleration, I might be able to find that in a force analysis. All right. Well, force analysis requires me to have an object, I already have it, and an interaction. Now, what are our interactions? Well, here's the bullet is the object. We know that there's a force of gravity on the bullet. That's between the bullet and the earth. So if I start to develop my free body diagram of the bullet, I have my force of gravity, which equals mg, which equals the weight, just as a friendly reminder. Okay, what else is the bullet interacting with? Well, it's sort of sitting in the barrel, so I might have the normal force between the bullet and the barrel. And the bullet's not moving up and down vertically. It is moving horizontally, but it's not changing its motion up or down vertically, so I might expect the normal force and the force of gravity to be the same. Okay, it's also being propelled, so there's a force out the gun. We'll call that the force of the gun. Let's say the explosion of the gun. So we have the bullet and the gun, and it's accelerating the gun down the barrel. So we'll call that the force of the gun. It tells us that that force in the problem is equal to 9,000 newtons. All right. Now, we're not given information about friction. We're going to then say, okay, well, there's no friction in this situation. And we can call this sort of force of the gun all the forces of the gun, the explosion and the friction, and it has an average force of 9,000 newtons to the right. So these are the only forces interacting with that bullet. So I number those forces. Oops. And I examine their components. So I have force 1, 2, and 3. And I can look at them horizontally, and I can look at them vertically. So force 1 is the force of gravity. Nothing horizontal minus the force of gravity. Force 2 is the force of my gun. Tells me that's 9,000 newtons. Nothing vertically. Force 3, that's the normal force. It doesn't have a horizontal component, but it does have a vertical component. Okay, so now I apply Newton's second law in each dimension, examining the forces in each dimension independently. So the sum of the forces horizontal is equal to the mass times the acceleration horizontal, and the sum of the forces vertical is equal to the mass times the acceleration vertically. Now I'm interested in the acceleration. This is a horizontal acceleration. This motion was all horizontal, so I'm going to start with that dimension. So 0 plus 9,000 plus 0 is going to equal the mass times the acceleration horizontally. Well, I'm given the mass of the bullet. 9,000 is equal to 0.01 times the acceleration horizontally. So if I solve for the acceleration, I get 9,000 divided by 0.01. That's pretty big force. Acceleration, 900,000 meters per second squared. So huge acceleration, very short distance, huge acceleration out the gun. I'm going to pause to pull up my key so I can give you. Okay, so we have 900,000 meters per second acceleration. And that, remember, was going to be used over here to give us the time, because I needed time and acceleration up here. All right, so I have 0.75 is equal to 1/2 900,000 times time squared. And when I solve for time, I find that that time is 0.0013 seconds. Bullets get out of guns pretty fast. So now I can not only input my time, but my acceleration up here in V final. So to be explicit, let's put those values into our list. 900,000 for my acceleration, 0.0013 seconds for my time, and I end up with the final is equal to 900,000 times 0.0013, and we find that our bullet is going 1,170 meters per second. Super fast, as we might expect a bullet to be traveling. All right, so what was our process? Well, solving that problem required us to look at kinematics. What is the final velocity? follow my kinematics process, and I discover that I need both acceleration and time. I can't get acceleration and time from my kinematics process, but I know I can get acceleration if I go to force analysis. Doing the force analysis, we find our acceleration. I didn't even care about the vertical dimension in this problem because all I needed was the acceleration horizontally, had enough information to do that. Using that horizontal acceleration, I could find my time. Knowing my time, I could find my final velocity. So again, linking force analysis through acceleration and solving for what we need. Good job.